Okay, hai. Assalamualaikum. Hari ni cikgu nak bincang tajuk 3.3 Electromagnetic Induction. Okay. So, describe electromagnetic induction. Electromagnetic induction is the production of an electric current by a changing in magnetic field. The induced current is produced only when there is a relative motion between the conductor or coil and the magnetic field lines. How induced current is produced? The relative motion of the conductor across a magnetic field can be produced by A. Moving a straight wire quickly across magnetic field between two flat magnets. Okay, so we have here a magnet or permanent magnet. This is north pole and this is south pole. So the parallel lines here shows magnetic field lines for the magnets. Okay, so direction is from north to south. And then we have a straight wire connected to a sensitive galvanometer. So a galvanometer is used to detect current that flow in the wire. So what we do, we move the straight wire through the magnetic field lines of the permanent magnet. So what happened is, when the wire is moved through the magnetic field of the permanent magnet, the wire will cut the magnetic field lines of the permanent magnet. The cutting off the magnetic field lines of the permanent magnet will produce changing in magnetic field of the permanent magnet. The changing in the magnetic field of the permanent magnet will induce EMF across the wire or will induce current that flow in the wire. Okay, so the changing in magnetic field induce current. So this is one example that we move the conductor or straight wire to cut the magnetic field lines of permanent magnet. Second example, moving a permanent magnet towards one end of a solenoid. So we have a solenoid connect to a sensitive galvanometer, and this is a bar magnet. The bar magnet has its own magnetic field lines or magnetic flux. So once you move the bar magnet towards the solenoid will cut the magnetic field lines of the bar magnet and produce changing in magnetic field. So the changing in magnetic field of the bar magnet will induce current that flow in the solenoid. Thus, the sensitive galvanometer will show deflection. So each time the straight wire cuts across magnetic field or the permanent magnet moves towards the solenoid, a current is induced in the coil and deflection is observed in the sensitive galvanometer. This current is called induced current. The electromotive force that produced is called induced EMF. So you must understand the concept of electromagnetic induction that states that induced current is produced due to the changing in magnetic field. How the changing in magnetic field can be produced? There must be a relative motion. Okay, based on these two examples, there must be movement or there must be a relative motion in order to produce changing in magnetic field. Okay, next page. Okay, we look at the situation. Situation A, straight wire. So what we do, we can follow the procedure here. Number one, hold a copper wire stationary between the poles of magnet. Observe the reading. What do you think? Is there any reading or not? If you just hold the wire between the poles of magnet, no movement. No movement means no relative motion. Of course, no change in magnetic field. Okay, so no induced current. So reading will become 0. Reading of the galvanometer is 0, pointing to 0. This is a zero-centered galvanometer. It's pointing straight up like this, meaning the reading is 0. Move the rod quickly in direction 1. 1 is upwards, 2 is downward, 4 is right, 3 is left. Okay, observe deflection of galvanometer. Repeat step 2 for other direction. So this one you can try when you can handle this activity in the lab, so you can observe deflection of the galvanometer. If a galvanometer shows deflection, it means there is an induced current produced. Current is induced in a straight conductor when it moves and cuts the magnetic field lines. The motion of the copper rod must be perpendicular to direction of magnetic field lines so that induced current will be produced. So to produce a very effective cutting off the magnetic field lines, the direction or the position of how you move the wire is perpendicular to the magnetic field lines, so that the cutting off is more effective or maximum, thus induced current will be produced. Okay, as a second example just now, in the case of a solenoid and a bar magnet, so you can carry out the same activity. First activity is push the bar magnet into the solenoid. Yeah, there is a relative motion. Of course, there will be induced current for this case. Okay, 2, hold the bar magnet stationary. Stationary means no relative motion. So in this case, no induced EMF or no induced current. So 0 reading, galvanometer. Now pull the magnet out of the solenoid. There is a relative motion. Okay, so meaning the pointer of the galvanometer will show deflection, but for this one, because you move the magnet opposite direction to the first one, so deflection also will be opposite. Okay, so galvanometer showed positive reading when the bar magnet and solenoid were coming closer to each other. So this shows that current is produced in the solenoid in certain direction. Okay, you get next page. Okay, so the conclusion is current is induced in the straight conductor when it move and cut the magnetic field lines. Current is induced in solenoid when there is relative motion between solenoid and magnet. So I hope you can get the idea about the electromagnetic induction. So you must know that there must be relative motion in order to produce change in magnetic field. When there is change in magnetic field, it will produce induced current. Okay, so how can we indicate or determine direction of induced current in a straight wire? So we can apply Fleming's right hand rule. So for Fleming's right hand rule, the thumb represents motion, direction of motion of force. The forefinger represents direction of the magnetic field, always pointing to south. The middle finger represents the induced current. Okay, so I hope you can use the Fleming right hand rule in order to determine direction of induced current. Look at the example here. A wire PQ is moved vertically downwards in the magnetic field. Applying Fleming right hand rule, the induced current will flow from P to Q. Okay, so this is north, this is south. So direction of the magnetic field is towards south, meaning left. Okay, move downward, so you mark direction of motion of force F downward. This is motion, or you can just mark as F lah. So you apply Fleming right hand, so point the forefinger towards south, force to downward, downward. Then what happened to the direction of the for the induced current is into the paper, or we can say direction is P to Q. So this is how we determine using Fleming right hand rule. Okay, now in this case, moving a wire to cut the magnetic field lines of the bar magnet or permanent magnet like this. So this one we can apply Fleming right hand rule. But for the case like solenoid and the bar magnet, we cannot use Fleming right hand rule. So we need to apply Lenz Law. What is stated by Lenz Law? So you need to memorize what is stated by Lenz Law. Direction of induced current in a solenoid is such that its magnetic effect always oppose the change that producing it. So it sounds a bit complicated, but try to understand by using example. Okay, you can look at next page. Okay, as example here, we have a ball magnet. This is north. You can see this is north, this is south, and here we have a solenoid. Magnet is moved towards solenoid. So when magnet is moved towards solenoid, before you move the magnet, the solenoid don't have any current. It shows 0 reading. But here drawn to you the pole here, meaning result of the activity, means after the ball magnet is moved. Okay. So when the north pole if moves towards end of solenoid here, let's say I put P here and Q. Okay, so the north pole of the ball magnet move towards NQ of the solenoid. Based on Lenz Law, direction of induced current in the solenoid is in direction that oppose the effect that produce it. What is the meaning of oppose? So when the north pole come towards Q, this NQ try to repel the ball magnet. So in order to repel, this NQ will become north pole. So when the NQ here is north pole, meaning P is south pole. Okay, so now based on the pole that you get for the NP and Q, you can mark the current that flow in the solenoid using right hand grip rule. Okay, so when we apply right hand grip rule for solenoid, so you will get direction of magnetic field. Right hand grip rule is like this. Okay, the thumb is pointing to north. The other 4 fingers represent the current that flow in the solenoid. Okay, so you have here all the current will move this direction. Okay, so meaning go down here, go up here. So direction of the current in the solenoid here from left to right, so deflection of the pointer will become right. Okay, so that's we call Lenz Law. So it's quite easy to know what pole for Q is. If the north pole comes towards NQ, so NQ will become north in order to repel or to oppose the effect. Okay. Second, the ball magnet move away. Okay, the ball magnet move away. Okay, so here is P, here is Q. Okay. So when move away, same thing. NQ try to oppose the effect. To oppose the effect that produce it, NQ will become south pole, meaning it try to attract the ball magnet. So it become opposite pole. Here will become south. If Q is south, then P is north. Then you apply again right hand grip rule for solenoid. So direction of current in the solenoid will become this direction. Okay, so meaning it will go up here and go down here. Okay, so direction of current that pass through galvanometer is from right to left. So the pointer will point to the left. So you can see here, when you move the ball magnet towards the solenoid, deflection is to the right. When you move away the ball magnet from the solenoid, deflection will be opposite, that is to the left. So this is how we apply Lenz law that states that direction of induced current always oppose the effect that producing it. Okay, so we can produce a conclusion like this. Lenz law for solenoid: relative motion between magnet and solenoid towards each other, away from each other. So polarity at the end of the solenoid facing the magnet, if moved towards each other, it becomes same polarity to produce repel force. If moved away, it becomes opposite polarity to produce attractive force. Okay, because it's trying to oppose the effect that produce it. So actually the Lenz law apply based on principle of conservation of energy. So Lenz law is an example of principle of conservation of energy. When magnet or solenoid is moved against the opposing force, work is done. Therefore, mechanical energy is converted to electrical energy. So the relative motion actually is mechanical energy. So in order for the energy to be transferred to other form of energy, work must be done. So in this case, work done against the opposing force. Thus, the mechanical energy is converted to electrical energy. So the relative motion actually supply mechanical energy. So then the mechanical energy convert to electrical energy. Okay, that one we discuss about direction. Now we discuss about magnitude of induced current or size of induced current. So we have one law, there is Faraday's law. The size of the induced EMF is directly proportional to the rate at which the conductor cuts through the magnetic field lines. Means how big the induced EMF produce or induced current produce. So you can see here the induced EMF directly proportional to the rate of change of magnetic flux or rate of cutting of magnetic flux. So the size of induced EMF, thus the induced current increased by moving the magnet or solenoid at higher speed. Higher speed means it will increase the rate of cutting. More lines being cut per second. Okay, increasing the number of turns on the solenoid. More number of turns also will cut more lines. Increasing the strength of magnetic field. Strength magnetic field is stronger, meaning there are more magnetic field lines which is closer to each other. So it will produce larger cutting off magnetic field or larger change in magnetic field. So these are the factors that affect magnitude of induced current. Okay, now let's discuss one example. Okay, show the correct direction of induced current when magnet is moved in the direction shown. Okay, now you see here, this is north, this is south. So north is moving towards the solenoid. Okay, so I mark here P, Q. Okay, now when north pole move towards P, according to Lenz law, okay, it will produce the direction of induced current that always oppose the effect that producing it. So when north pole comes toward P, P will become north pole. Okay, remember, move towards becomes same pole, and Q will become south pole. Now you apply right hand grip rule for solenoid. Okay, so meaning direction of the current is like this. Okay, so meaning here it is. Okay, so direction of the deflection of the pointer from right to left, so meaning the pointer will deflect left. Okay, second example, north pole move away. Same thing, if move away it become opposite pole. Here will become south and here will become north. So you apply right hand grip rule for solenoid. Direction of current Direction of current is like this. So current flow through the galvanometer is from left to right. Thus this one deflect to right. So you can see deflection is opposite because direction of induced current is opposite. Okay, now south pole, move towards end of the solenoid here. Move towards become same pole. So here is south, here is north. Okay, so apply right hand grip rule. So direction will be like this. From left to right, so deflect right. Okay, knee move away, so it become opposite pole. Here is north, here is south. So direction of induced current, the solenoid, become like this. So from right to left, deflect left. Okay, so we apply Lenz law to determine direction of induced current. So this one, direction of induced current is determined by deflection of the pointer of galvanometer. Okay, now let's look at this example. What is direction of induced current? For this case, straight wire, move down, direction downward. Move down. This is north, this is south. So you apply Fleming right hand rule. So you will get the current is flowing out from the pepper. Okay, is it correct? North to south here, downward. Okay, it's moving out from the pepper. So meaning direction is like this. Okay. So for this one, determine the pole for P and Q. Now given direction of current. Current is out, motion is upward. So you apply also same thing. Fleming right hand rule, direction downward. You put your thumb upwards. Okay, current out. Okay, so current is out. Current is out. So meaning the point, your forefinger is pointing to the left. Pointing to the left means P is south. So Q is north. Okay, so this is how we solve problem by using Fleming right hand rule. Okay, so I will continue on the next lesson about application of electromagnetic induction. So I hope you can go back and do more revision on this topic.